Hello, this is NCWIT Collegiate Award Application number 234360, and I did my project on TracKnee, a knee angle measurement device using stretchable conductive fabric sensors. The knee is the most commonly injured joint, at 2.29 knee injuries per 1,000. These knee injuries mostly occur in younger athletes. These knee injuries often require extensive physical therapy, and in order for them to keep on track with their recovery, the patients must remain vigilant about their knee movements even outside of physical therapy. We can use wearable technology to help them collect data outside of a clinical setting. This body motion tracking has greatly impacted advancements in medicine. Furthermore, joint angle estimation is an important part of managing and tracking the progression of diseases, including but not limited to osteoarthritis and Parkinson's disease. Consequently, measuring human body joint angles is receiving an increasing amount of attention from both the medical sciences and computing disciplines. This research will enable researchers to collect more data in the real world, which is important when treating diseases. Soft, flexible, wearable e-textile sensors allow for the comfort of the wearer while simultaneously allowing the collection of important biometric data. The primary modeling technique used in this experiment is a regression model, which is a form of predictive modeling which investigates the relationship between a dependent, which is the target, and independent, which is the predictor. There were three things that were modeled in this project: the knee angle to length movement, which is on the top left, which resulted in a linear regression model, the length to resistance, which is on the top right, which resulted in a third-degree regression polynomial, the resistance to voltage, which is on the bottom middle, which resulted from the need to get resistance variation from the voltage charge. All of these models were coded using scikit-learn machine learning in Python. The next project was to create the device. The first part of the project was creating the control patch, which contains all of the non-washable electronic components. The second part of the project was creating the sensor sleeve, which contains the fabric sensor. This part is able to be washed. And when these two parts are connected, we have a full TracKnee prototype, which is shown on the left. Afterwards, we developed an application to help collect data from our TracKnee device. The application had 4 total states. The first state was the initial state, which is shown when the application is launched. This state has 2 main components: a timestamp and subject ID number. The timestamp is displayed throughout the entire application, and the subject ID number is a field where the user can input the number that is assigned to each subject. Once this field has been completed, the user can press the scan button to move the application into the second state. The second state is the BLE scan state. The application scans for Bluetooth low energy devices. If the Bluetooth is correctly connected and the application is receiving data, the application moves to the third state. If the application does not connect to the device, it returns back to the initial state. The third state is the BLE connected state. In the BLE connected state, the background of the logo changes to green and the scan button becomes connected. During this state, if the Bluetooth device disconnects, the application returns to the initial state. If the user connects the application to the wrong device, this is the time when they can go back and change it. And finally, the last stage is the collection of the data. Once the user decides to collect the data, they must press the Start Data Collection. Once this button is pressed, the application proceeds to the fourth and final stage, which pops up a toast message, and then also logs the data onto a CSV file that contains the timestamp and sensor information and is named with the subject ID and the corresponding time. The final step was to create models to determine the accuracy of our device and app. We used an intuitive model and a linear regression model to model our data. First, we created our regression models. We created 3 models off of the groupings of height, and we were able to create a second-degree regression model shown on the screen along with their equations. The intuitive model is just a simple ratio. In this table, we show the accuracy for each model on each group of experiment participants. From these results, we can see the regression model outperforms the intuitive model at all 3 height groupings. Overall, we were able to reach an accuracy level up to 89%, which is very close to the 95% accuracy required for a model to be considered medical grade. In the future, this device will be able to help advance the medical field by helping monitor and maybe even prevent knee injuries in the future. Thank you so much for listening to my presentation.